The Heisenberg uncertainty principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning. To understand this, we need to think about what it means to behave like a particle or a wave. Particles, by definition, exist in a single place at any instant in time. We can represent this by a graph showing the probability of finding the object at a particular place, which looks like a spike, 100% at one specific position, and 0 everywhere else. Waves, on the other hand, are disturbances spread out in space, like ripples covering the surface of a pond. We can clearly identify features of the wave pattern as a whole, most importantly, its wavelength, which is the distance between two neighboring peaks, or two neighboring valleys. But we can't assign it a single position. It has a good probability of being in lots of different places. Wavelength is essential for quantum physics because an object's wavelength is related to its momentum, mass times velocity. A fast-moving object has lots of momentum, which corresponds to a very short wavelength. A heavy object has lots of momentum even if it's not moving very fast, which again means a very short wavelength. This is why we don't notice the wave nature of everyday objects. If you toss a baseball up in the air, its wavelength is a billionth of a trillionth of a trillionth of a meter, far too tiny to ever detect. Small things, like atoms or electrons, though, can have wavelengths big enough to measure in physics experiments. So if we have a pure wave, we can measure its wavelength and thus its momentum, but it has no position. We can know a particle's position very well, but it doesn't have a wavelength, so we don't know its momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other. The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger, a fourth and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty. That's the Heisenberg uncertainty principle, first stated by German physicist Werner Heisenberg back in 1927. This uncertainty isn't a matter of measuring well or badly, but an inevitable result of combining particle and wave nature. The uncertainty principle isn't just a practical limit on measurement. It's a limit on what properties an object can have, built into the fundamental structure of the universe itself.